My name is Angus Nicholson. Thank you for coming to this talk on explaining explainability, recommendations for effective use of concept activation vectors. Excitingly, this work was recently accepted at the beginning of 2025 to Transactions on Machine Learning Research. So a quick summary of the overall paper. In general, what we're interested in is a method called concept activation vectors, which are used to generate concept-based explanations for deep learning models. We studied three different properties of CAVs. They cannot be consistent across layers, they can be entangled with other concepts, and they can be spatially dependent. We provide tools to analyze each of these properties and show they can each affect testing with CAVs. In other words, they can affect the explanations you generate from these CAVs. We then provide clear recommendations for researchers and practitioners to help sanity check their CAVs and demonstrate how to use them on a melanoma classification task. We also release a configurable dataset called Elements to aid in the study of concept-based explanations. First of all, what is testing with concept activation vectors, or TCAV for short? TCAV explains deep learning models in terms of concepts. And concepts can be a variety of different types and defined by the probe dataset of concept examples. So they could just be textures like striped, spotty, or banded, color, some kind of shape, or even some kind of more complex context-dependent object like a wheel of a car, a window, or the shape of a specific structure in the brain. Or they don't even need to be image-based. For example, there's some work analyzing how different chess tactics are learned by the reinforcement learning algorithm AlphaZero, which uses CAVs and TCAV to help understand this. But what is a CAV? So you create a CAV by passing through images through your model and extracting the activations in some sub-layer of the network. You then train a linear classifier on these activations, and the vector orthogonal to the decision boundary of that classifier then is your CAV, this VCL over here. And so we have in this case, we have the activations of your stripy images and activations of your random images, and the decision boundary between them, and then your vector now points towards these stripy objects. So your vector kind of represents stripes in the activation space of this model. Okay, that's how we generate the vector, but then how do we actually get an explanation out of it? That's where testing with CAVs comes in. So box A, C, and D are the same here, but we've got some additional things going on. Mainly the most important bit is down here, E. This is kind of a representation of something called the directional derivative, and that is the actual kind of measurement of how sensitive the model is to a specific concept for a specific class. So in this case, we're interested in the class of a zebra. And so we'll pass some zebras through our model and look at the logit of the kth class, in this case, the class representing zebras. You then calculate the derivative of the logit with respect to the activations in the layer where you created the CAV. And that's this gradient down here. You take the dot product of the gradient with your vector, your CAV, you then get the directional derivative. And now our directional derivative is the key kind of value for the sensitivity of the model. And intuitively, you can see it as if the activations were to move in the direction of the CAV vector by an infinitesimal amount, then how would the logit change for that class? We don't just use the directional derivative in its raw form, we actually can binarize it and also take it across a whole range of images. So the TCAV score is a proportion of the validation images for which the target class has a positive directional derivative, i.e. This suggests that the model is positively influenced by that concept. Actually, to kind of help with some of the analysis, we analyze multiple CAVs for each individual concept, and this allows us to do some significance testing. So for example, in most of the paper, we test 30 different concept vectors for the same concept, and then compare that to random vectors. So these are CAVs created from just random images on both sides of that decision boundary. And you can do a two-sided t-test for whether the TCAV scores of the concept and of the random CAVs are the same or not. And so in the bottom right, we have an example of a figure where we represent TCAV score for different concepts in our elements dataset. And the way you might read one of these, we don't really care about the kind of message of this image right now, but the way you might read one is, in this case, the x-axis shows different concepts, the different bars and colors are different layers of the network, and then the y-axis shows you the TCAV score. And these small little horizontal black dashes near the middle, near 0.5, is the null score, which is the average score of the random calves. And so the red lines here are where the TCAV score of our 30 concept calves were not significantly different from this null. Whereas, for example, the square concept here has a very high importance or high sensitivity for the model in a positive manner, and the triangle concept here also has a high importance, but in a negative manner because the scores are very low, whereas kind of a score nearer 0.5 indicates low importance or low sensitivity to the model. Now we have our elements data set, and this is quite a simple data set we created, but it's very configurable, and we create new images very quickly. Each image just depends on a few different properties like the color, brightness, size, shape, texture, and the number of shapes, and so on in each image. The reason we found this data set useful, it allows us to create lots of different images which we can generate on the fly, which is very useful for creating probe data sets. So for example, we can create more complex ones, like on our right there, we've got the striped objects on the left of the image and striped objects at the right of the images. Using this data set, it's very easy to create these different kind of concept probe data sets to create your calves. The other important thing is we have a known ground truth. So we know the causal relationship between each concept and class, and we know which concepts are present in each image and where they are. What this allows us to do is when we train a model with a very high accuracy on all the classes, we know the model is using each concept correctly. So if we see a strange explanation coming out of our explanation method, we know it must be something wrong with the explanation method rather than something wrong with the model, because the model has to be using those concepts correctly to get all of these images correct. So now we get on to the properties that we're interested in. First of all, let's talk about layer consistency. So intuitively, we wanted to ask, do calves in different layers mean the same thing according to the model? To do this, we tested whether they have the same effect on the model. Short answer is they don't, but let's go through it. So on the right, this scary looking diagram, we start with the activations in some layer L1, and F is a function to go from layer L1 to layer L2. So for example, that could just be, say, a convolutional layer and a ReLU or something like that. And we pass the activations through that layer to then get the activations in layer L2. And then following the green path, we then add the vector, the cav that you created for layer L2 to get the perturbed activations in layer L2. What we wanted to know, if you go down a different pathway, do you get the same perturbed activation? So if instead we add the vector in layer L1 and then move on to the next layer using F, do we get the same outcome no matter which pathway we go on? To kind of measure this, we use the consistency area, which is the difference, the L2 norm of the difference between these two pathways. And we get a non-zero consistency error, which is kind of to be expected. We actually have some a theoretical proof in the paper demonstrating the requirements to be able to get a zero error in this case. And actually for the models we looked at, even when we optimized for consistency, so where we fixed the vector in the first layer, but in layer L2 we just did a gradient descent to try and minimize its error, you couldn't find a cav with minimum error. We speculate that the reason you have inconsistent vectors between different layers is because actually each cav represents slightly different versions or aspects of the same concept. The reason this actually is important is because sometimes you obtain very different TCAV scores for different layers. So on the right, we've got two different examples, one for the elements dataset in the top, where in this case, the cross concept has a quite high sensitivity in layer 3, but a high positive sensitivity, but a high negative sensitivity in layer L4. So these two adjacent layers basically tell us opposite things about sensitivity of the model. And that's very difficult to interpret until you start thinking about this, and actually maybe just is the cav you created for cross, it means slightly different things in those two different layers. Or down here for ImageNet, we've got for multiple different classes, the sensitivity of the striped concept. And we can see in this case, we seem to have a much higher sensitivity in this layer 4.1, the penultimate layer of a ResNet 50, compared to the earlier layers in the network. And we did some additional experiments, which are in the appendix, where we looked at Deep Dream to try and kind of visually represent the different aspects of the concepts that these CAVs represent. And so this was actually the Deep Dream visualizations for the car concept. And you can see in the earlier layers of this ResNet, we see much smaller kind of boxy shapes coming out of the Deep Dream, whereas in the later layers of the network, you can see almost whole bits of car or whole cars in this visualization. And this isn't very quantitative work, but we just kind of wanted to add some visualizations to some of the discussion. Moving on to the next concept, we have entangled concepts. So it's not surprising that concepts are associated with each other. This is not a novel statement. An inherent part of the sky is that it is often blue and often contains clouds. So we should not expect the concepts of sky, blue, and cloud to be entirely separate. However, we think it's important to discuss the consequences this can have and the misleading explanations you can obtain. We created 3 different versions of our elements dataset with an increasing association between the red and triangle concepts. So the first version of the dataset, each combination of color, shape, and texture is equally likely. In the second version of the dataset, the only shape that is red is triangles. And in the third version of the dataset, the concepts of red and triangle only ever co-occur. We then just use the cosine distance between CAVs to measure the similarity between them, where in this case a positive 1 means these vectors point in the same direction, 0 means they're orthogonal, and -1 suggests they point in opposite directions. And this is what we obtained for those 3 different data sets, moving from left to right, showing each of the similarities between all the different concepts in the simple version of the elements dataset. Actually, I'm going to bring your attention to the red box that I've highlighted here, because this shows the triangle and the red concepts. And we can see for the first data set, these concepts are almost orthogonal with a 0.06 similarity, whereas in the second data set, you have a 0.3 similarity, and in the third data set, you have a 0.53 similarity. So increasing similarity between those concepts as you increase association between them. Makes sense. But actually, in that last data set, we see the triangle and the red concept are actually just as similar to each other as they are to themselves. And you might ask, why do we not have a similarity of 1 across this diagonal? That's actually because I talked earlier about how we train multiple CAVs per concept. And so in this case, we train 30 CAVs. And this shows you the similarity between those different training runs. So actually, if you train multiple red concepts and look at the similarity between them in this data set, there are only 0.55 cosine similarity. But what does this actually mean for the explanations? So if we look at some TCAV explanations for the class of striped triangles, we can actually see some misleading explanations for that second data set, where the concept of red comes out as, the model comes out as being sensitive to that concept. When we know the model is not using this concept, because the model gets something like 99% accuracy on all the different classes, and so suggests that the kind of association between this red and the triangle class has artificially increased this TCAV score. Also, interestingly, we had a look at these kind of blue sections of the plot, and we saw that in this case, mutually exclusive concepts turned out to be anti-correlated. So the model didn't just learn that green means green, it learned that green means not red and not blue as well. And the third and final property we're interested in is spatial dependence. So to train CAVs, we typically flatten the activations into a single long vector. So we have, in a convolution, activations of height by width by depth number of channels. We flatten that into one long vector of height times width times depth. So it means each element within the activation actually depends on the location it came from in the activations. And we hypothesize this can lead to some spatially dependent CAVs. And we tried to visualize this by using spatial norms. So we took the L2 norm of each 1 by 1 by d depthwise slice of the CAV. And if the spatial norms vary substantially across the height and width dimensions, then we consider the CAV to be spatially dependent. And if we look at the spatial dependence of multiple CAVs across different training runs, we actually see it does look like there's some spatial dependence going on these different training runs. But if we average these across, we actually find this disappears. So if you look at the top row of this diagram on the right, this shows you the average L2 norms for the striped concept in multiple different layers of the elements dataset. And we see there's no real spatial dependence in that top row. But interestingly, we can actually intentionally create some spatially dependent CAVs by using spatially dependent probe datasets. So, for example, we use probe datasets where the striped objects only appeared on the left, and that allows us to create CAVs which only have norms on the left part of the activations. What this allows you to do is actually do tests for spatial dependence using TCAV. So in this example, we created a version of the elements dataset which had spatially dependent classes. So for example, this class was striped triangles on the left. And then we created CAVs of all the different types, both spatially dependent and not spatially dependent, and observed differences in their TCAV scores. So in this case, triangle and triangle left come out as very highly positively sensitive, whereas triangles right is much closer to 0.5, it's suggesting much closer to null, suggesting not very sensitive to the triangle right concept. And similarly for stripes left and stripes right. This is exciting because it means you can actually test for translation invariance to specific concepts and specific directions in your model. We also found some evidence that this exists in more complex data and models. So for example, for ResNet 50 on ImageNet, we saw an example where for the clownfish class, we observed, i.e. Nemo, we observed that the model seemed more sensitive to water at the edge of the image than water in the middle of the image. So now we move on to the recommendations that we have for using CAVs in a safe and effective manner. First of all, we're going to start with consistency. So you should create CAVs on multiple different layers so you can determine whether the TCAV score is fluctuating or changing amongst those layers. We should also, for entanglement, verify that there are expected dependencies between related concepts. And be mindful that when you obtain a high TCAV score, it may be due to some kind of concept entanglement rather than to sensitivity to that specific concept. And then finally, for spatial dependence, we should visualize concept-vector spatial dependence using spatial norms. It's worth bearing in mind that our visualizations are necessary, but certainly not sufficient tests to verify that TCAV is working as expected. In the paper, we actually go through some recent papers that use CAVs but don't check if these properties affect their results. And in much greater detail, we go through a specific use case analyzing a melanoma classification task. So in the paper, we show that medical explanations cannot be, in this specific case, cannot be interpreted. And we improve the explanations for some of the spurious correlations that they analyze. This analysis that we have in the paper can be used as a template for practitioners to validate their own results. I'm just going to focus on this kind of first bullet point for this talk, just for time reasons. So I've got two different sets of similarities between different concepts in this data set that I visualize here. On the left, if you analyze here, look, there's multiple different pairs of concepts. So for example, regular vascular structures, irregular vascular structures, and typical pigmentation and atypical pigmentation. That's because each concept came in three different categories. It was regular, irregular, or absent. And so what we decided to do, we followed the paper that we were looking at and used the absent label as the negative probe data set for each of these CAVs. And then generated the TCAV scores and the CAVs accordingly. Also, as a comparison, we did the same thing, but where we used random images as normal for the negative probe data set, and that's what you can see on the right of the screen. Interesting, what we found is when we use the absent labels, we found a very high similarity compared to the rest of the CAVs between concepts of opposite meaning. So for regular vascular structures, the concept that is most similar to that compared to all the concepts that are present was irregular vascular structures. And same thing for each of these other pair of concepts. And when we use the random ones, that's not the case. Actually, these concepts seem to be close to orthogonal. And this was a little worrying and actually shows something quite important, that your choice of your negative probe set is actually substantially changing the meaning of the concept. And in this specific case, we think it means you can't use the absent label as the negative probe set, because it's this high similarity between opposite meaning concepts suggests that these calves don't mean what you think they mean. So we need to use the random labels for our calf in this case. The problem with doing that is when we look at the accuracy of the calves, so how well these linear classifiers in activation space classify the activations of your concept versus random, we actually see very low accuracy. So on the right here, we have the accuracy of these different concepts, these different calves, trained with the random label. On the left is for the absent label, but as we already discussed, we can't use that, so we need to use these ones, and then these ones have very close to 0.5 accuracy, which means they don't mean anything. So actually in this specific case, we don't think you can use calves for any of these medical concepts that we've got. We can actually still look at some of the spurious correlations like dark corners, dark borders, and ruler, and we go through into more detail in the paper, so please go have a read if you're interested. So a quick summary of the overall paper. Concept activation vectors are used to generate concept-based explanations for deep learning models. We studied 3 different properties of calves. They cannot be consistent across layers, they can be entangled with other concepts, and they can be spatially dependent. We provide tools to analyze each of these properties and show they can each affect testing with calves. We then provide some clear recommendations for researchers and practitioners to help sanity check their calves and demonstrate how to use them on a melanoma classification task, and release a configurable dataset elements to help aid in the study of concept-based explanations. A big thank you to my supervisors, Alison and Yaron, and my collaborator, Lisa, also to various funders and organizations. And now will be when I'd ask for questions, but this is a pre-recorded video, so please check out the paper at OpenReview to that QR code in the bottom right. And feel free to reach out to the email on the paper if you have any questions. Thank you for listening.